All right. Hello, everyone. So, Davide, do you want to share your slides? Then make sure we can get started. No problem. We'll wait.
Recording in progress.
Hello, sorry. Hi, everyone.
All right, great. So, wow, that was interesting. Okay.
Let me share my
Share your
screen.
screen. Perfect. Okay, so let's get started. Great. So welcome everyone to another OCP Tap session. This is call number 95. Wow, 95. 95, 2 weeks since we started. And today's speaker is Davide Rovelli. Davide is a PhD student in the SWY-STEMS group, led by Professor Patrick Uxter at USI, which stands for Università della Svizzera Italiana. He's also a research collaborator at SAP's Cloud Innovation Office. His work focuses on deterministic data center layer, which is a set of low-level software and hardware systems to provide timely interactions, which are used to optimize and simplify distributed systems. So today's talk is about reliable and fast failure detection with deterministic interaction in data centers. And with no further ado, Davide, the floor is yours.
Thank you very much. So first, thanks all for the opportunity. I'm really thrilled to be here. Yeah, as Ahmed says, I'm a second-year PhD student at the Systems Group and also work at SAP. Today I want to talk a little bit about my research, which latest works concerning reliable failure detection using synchronous interaction. So that's what I'm going to tackle for the most part of the presentation. And then in the last few slides, I am going to talk a little bit. I have some let's say some pointers on some common grounds with the time appliance project which I have to admit I'm not too familiar with at the moment. I have just recently started knowing Ahmad and the work of the community. So it would be really interesting if we could have a discussion and we can find some common working points on this topic, which is of great interest of myself and also of our group. Okay, just before starting, I had a little change on the presentation title. I will use the word synchronous instead of deterministic, which mean the same thing in this context, but I switched to the former for more clarity, and perhaps you'll see why later.
And also one more thing, if I may ask, please, everyone, I see a lot of microphones that are not muted. Please mute your microphones so as we go through this wonderful presentation, we'll not have that much noise. Thank you, everyone.
Thanks for that. Okay, so let's start with a little bit of background. I think I don't have to explain you that distributed systems are everywhere. First and foremost, for performance after the end of the scaling, we cannot put more transistors on the same area. So everyone has started switching to distribution in terms of hardware and how to optimize the distributed computation. But also we have other types of distributions. We have distribution by requirement, such as fault-tolerant services, replicated services, or distribution by design. So we can design a software application as perhaps the very famous microservice design pattern. Just so our work is, and our lab works on distributed systems, and we'll see later on more on cloud systems. Just a little note, we don't intend distributed systems at HPC. Sometimes it comes as confusing. So basically our distributed systems, as I said before, have different requirements. They're not just fast, but we want them to be reliable and transparent because they're usually user-facing. While HPC is mostly fast and adopting massive parallelization of scientific workloads, both of these disciplines focus on efficiency, be cheaper, less energy and resource consuming. But we have this whole reliability, availability side to it with respect to HPC, which shifts the focus quite significantly. And an important information is that our work focuses on data center scale. So we want to improve distributed systems at the data center. So as I said, cloud services have high availability and reliability requirements. We are talking about 24/7 user-facing services, which so I just listed some examples of some concrete services that you might be familiar with, such as Redis etcd, ZPDB, and Memcached, which I believe are from Meta, as replicated key value stores, databases, and of course, we have clock synchronization, and I don't think I need to introduce that to you, which can be used for replication and updates and many more of these highly available services. So to achieve such high standards and high requirements in availability and reliability nowadays, we need both performance at the same time as fault tolerance and consistency. So there's a few ways to achieve that, and it's certainly through distributed coordination protocols, but also a very crucial part, a very core part of this is reliable failure detection. The two things, coordination protocols and failure detection, are overlapping, but in this presentation, we will focus mostly on how to reliably detect failures. Right, so let's first start from the definition on what is a failure detector. So we intend a failure detector as a self-contained layer or set of components that is monitoring process failures and signaling them to other monitoring processes. So we have a group of processes that's interested in knowing the health status of other processes, and we can employ this layer, which we call a failure detector, which is usually abstracted from the main process or the more monitoring process. So what is a good failure detector? Well, we have two characteristics, and these are the two properties of the two most important properties of failure detector and of our specific design. So first and foremost, we have reliability. So a good failure detector does not signal or suspects, in more formal language, processes which are alive, and we call this false positives. And we can see that in the diagram of the right. Hopefully you can see my mouse pointer. So on the top diagram, we see, so it pictures a typical scenario of a primary backup. So requests come into a node P, and then are replicated to the backup replicas. And this simple algorithm does this primary backup. So a reliable failure detection correctly signals the failure of the primary. And then we have let's assume a simple algorithm that says that P1 becomes the new P every time there's P is flagged as failed. So this is what happens with a reliable failure detector. On the other hand, on the very same scenario, a reliable failure detector, as we said, can have false positives. So it can wrongly suspect a process to have failed. So what can happen here? We have the same algorithm as before, and B1 is going to become the new P. So now we have two Ps at the same time, which can perhaps break the consistency or break some guarantees of our service. So this was meant as a very basic example of just underlining the importance of reliability in a good failure detector. And of course, then we want a failure detector to be fast. We're talking about microsecond scale for modern microsecond apps and for modern data center speeds. In these slides, there's a more, let's say, formal classification of failure detector. So this is just to show that we can have different degrees of reliability based on accuracy that can be simplified as having no false positives, as mentioned before, and completeness, meaning as all failures are detected. So we can have different degrees of these reliability. And we do not need necessarily a perfect failure detector, right? We can also use more unreliable failure detector and just build more robust algorithms on top of that to achieve our consistency guarantees. However, the weaker the failure detector, the higher the complexity of the algorithm that needs to, let's say, compensate for the poor reliability of the failure detector. So what the goal is, we'd rather have a reliable failure detector because a reliable and fast failure detector enables simple and efficient services. But the big question is how to build one. We have two ways of doing failure detection, which are pretty intuitive. So the first method is active failure detection. And we have that when a failure detector process monitors another process and sends a notification when it fails. This method, it can be very fast, but can also be incomplete. So what happens if the monitoring process, if the failure detector process fails? We will never know that an application is actually failed. So this can be incomplete, and there's workarounds, and we'll look at some of them. But generally, it is like that. And then there's the classic failure detection mechanism, which is the heartbeat or passive failure detection. So basically, a failure detection monitors a process and keeps sending heartbeats to other failure detection processes. So when either the application or the failure detection process fails, other processes will time out. And if they don't receive 2 successive heartbeats, let's say. And a timeout means failure and covers and is therefore complete, but possibly slow. But here we come to the real problem. How do we set these timeouts? Okay, so in a failure detector, at some point we'll have to set a timeout, right? And this is a problem because what value can we use? So in literature, in current literature, is distributed systems are considered as synchronous, meaning that a process interaction, and by interaction I mean both the communication latency and the processing latency of the message at the end host can take any time. So a message is when in our C code we call the send method, and then a message is sent, and to when it's received from host B is basically we assume that it can take any time. And why is that? Simply because of resource contention on both the servers and the networks. So at the processing side, we know that servers are complex multitask systems. So we have a whole bunch of things going on at the same time, such as operating system context switching, interrupts, PCI jitter, NIC queue congestion, and other factors that can basically impact the reaction time of the failure detection to a received message. The same problem of resource contention is also shared by networks, because networks are also shared, and clearly we can have network congestions, we can have switch and link failures that all can delay due to rerouting perhaps a message, and therefore we come to the fundamental problem, which is asynchronous interactions are not really a good fit for timeouts, are not really a good fit for failure detection, right? So you can see in the simple diagram, for example, process P sending a message to other processes to just know who was alive, and in a very simplified monitoring algorithm. So we send a message, broadcast a message to all processes, and then one of them crashes, so it's effectively not alive anymore. But the great question is here, when do we determine? So this message is quick to arrive, so we know that Q is alive, but if we decide here at this green point that we should have received all the answers, then we are incomplete. We didn't detect S. If we decide here, then we detect both Q and S. So with this very simple example, you can see that if we have arbitrary length interaction in messages, we can it's very difficult to establish a simple protocol such as this one. So this is the fundamental issue. What timeouts do we use? Larger timeouts lead to poor performance. Smaller timeouts lead to poor reliability. So I'm going to outline now the approach of some of the state-of-the-art failure detectors that try to overcome this unpredictability of the system, unpredictability of interactions. And pardon me, the most let's say recent category of failure detector can be classified as multi-level failure detector, and they can be seen in this picture here, the architecture of Falcon, which is the name of the most relevant algorithm failure detector in the area, the most famous up to now. So these failure detectors have two characteristics. They are system tailored and they use internal observation. So what do I mean by that? Basically, in order to have a prompt failure detection, these systems riddle the monitored system with spies or probes. So they deploy multiple observers in each layer of the stack they want to monitor. And then they build a hierarchy to ensure that the application spy will detect a failure of the application and report immediately to the client failure detector. But what if the application spy fails? Then there's the OS spy that monitors it and that monitors the layer. So it can flag that the application spy has failed so that the failure detection can perform an action, and et cetera, in this hierarchical manner. Internally observe every element of a given system in order to be fast in detection and as reliable as possible by monitoring as many probes as possible. So the pros of these methods are we can define a custom failure model, right? So we can decide that this application here, app1, is down when it becomes unresponsive. So that's a pro because we can define the logic in our spy. And another approach is quick detection and response through internal observation. However, the downsides of this approach is that such failure detection are complex and they indeed introduce more points of failure. So basically, this system of probe monitoring probes is infinite. It doesn't have an end. So you can always have a probe monitoring another probe, another layer, and et cetera, but you can never prevent the case where there's some probe not monitoring another probe that fails, and then the failure will go undetected. And in that case, these systems still rely on large unstable timeout for worst case. So we argue that these systems do not tackle the fundamental issue of unpredictable interaction, which is a major impediment in the system, and it's not solved by riddling the system with probes. Hence, we propose our approach, which is the main topic of this presentation, which is a system-driven, reliable failure detection. So what does that mean? We use ground-up data center systems to support to, first and foremost, establish synchronous end-to-end interaction. Again, interaction meant as network and processing delay when we send a message. So we want this interaction to have an upper time bound. Okay, we want them to be synchronous, to be reliable. And secondly, we want to use external observation with the help of the operating system to have a single failure point instead of problematic multiple probes, as I was saying before. These design goals enable a robust and reliable failure detection system, and fast. Also, yes, we will see it later. So the main challenge in having this design is how to build synchronous interaction. Okay, so to do so, we have to overcome network jitter and end-of process jitter, which is a very hard task in a data center. And this was the original reason behind having the asynchronous assumption of the message that will be eventually delivered. But we start from this and we take different observations. So the first observation is that we don't need the whole system to be synchronous. We don't need the whole interaction to be synchronous. We need only the failure detector. Okay, some applications are just fine with asynchrony, but it's just our application that would benefit from synchronous. So we can confine the synchronous to our failure detection. And the second observation is that data center hardware and software is becoming very diverse and very programmable, which provides unprecedented acceleration. So what if we use that to increase interaction stability or synchrony instead? And the last observation is that eventually we need to use timeouts, no matter what, for a good failure detection. So we might as well start focusing on achieving tight timeouts and reliable communication, reliable interaction as a first and foremost design goal. And now I'm going to outline how we managed to build synchronous interactions. So first of all, we want to achieve a stable network communication. I'm going to go a little faster here, so please interrupt me or ask me later if you want to know more details about this. So basically, we deploy failure detector processes to monitor one or more application processes. You can see here in the diagram, blue processes are failure detector processes, and orange circles are application processes. So what we do is that we have a custom SDN-assisted periodic multicast protocol. This protocol is based on traffic engineering techniques that minimize traffic interference. So what this protocol does is that it builds multicast tunnels for monitoring groups that are reserved and engineered to minimize interference at the maximum. So basically, we have a set of resources that our traffic engineering protocol gives to a transmitting process. And an example workflow is a failure detector process asks the SDN controller to monitor a number of applications within a given period, because our protocol is periodic for the heartbeats. And then the traffic engineering computes the tunnel, the multicast tunnel, and it might return a larger period because of interference. So we might have larger periods, but we always guarantee that there's no interference, that there can never be high jitter with existing tunnels. And then the second challenge is achieving stable processing time. So we want to react promptly to packets, which this task is often the most jitter-prone part of the interaction, even more than the network, because networks are becoming faster and faster. But the reaction of the operating system of a thread when it receives a packet can result in huge spikes because of operating system induced jitter, such as scheduling interrupts, etc., etc. So we use system support to minimize it. We have an isolated core, which is on the CPU, which is dedicated for failure detection and is shielded from interrupts of any kind. So it runs uninterrupted and reacts to failure detector messages as fast as possible. Then we use an LKM, a Linux kernel module, for reliable sending, bypassing the kernel stack. And on the receiving side, we use eBPF XDP pipeline, which is a kernel bypass method to receive the packet as soon as possible. And we also reserve queue in the NIC. I forgot to mention it here, so that we never have queuing on the receiving NIC side, and we have an interrupt that goes straight to our isolated core that can immediately react to the received message. The second goal is have external observation for reliable detection. So as I mentioned before, riddling the system with probes is flexible, but harms reliability simply for the fact of having these multiple probes. Instead, we want to use a single point of view, a single observer. And we only focus, and this is important, on process crashes. So we have implemented this through an operating system watchdog, which detects a failure even before the operating system it defines that process has crashed. And it does so by using simply a kernel probe, which executes. So our code executes just before the operating system function that determines that the process has crashed. And this is the whole picture. So we combine active and passive failure detection to have a complete system. And also we have this notion of this split system, which we reserve synchronous interaction exclusively for failure detection. The important thing here is when we detect a failure in the passive detection, so when the operating system crashes, we stop sending a heartbeat and we will detect the failure in phase 3. So, but we also have the active detection method, which allows us to send a quick notification to the monitoring process. And I'll avoid going through all the phases, but the important thing is here we use synchronous interactions to enable reliable failure detection exclusively for our failure detection processes, and through this system support, which allows for very good performance, as it can be seen by the results. So briefly, we managed to achieve with these systems stable and reliable interactions over several days of benchmarkings of more than 2.2 trillion packets, achieving a maximum latency of 45 microseconds. So our interactions are effectively stable. You can see how the blue line, which is our failure detection, stabilizes after the black dotted line, which is 45 microseconds, while other systems, other state-of-the-art systems, have jumps, because they don't focus on having stable interaction. And by doing so, through this stable interaction, we also managed to achieve very fast failure detection latency, because through the same system that we use to achieve stability and synchronous interaction, we also achieve speed, because it's reserved and it exploits the system properties to send packets reliably and in a timely manner. So our failure detection results in 4 times average improvements and 7.2 times improvements with respect of the worst case state of the art. And we have a very, very low, of course, worst case timeout, which is not the focus of other failure detection. So we are much better also in worst case scenario where the operating system and everything else crashes. Okay, so this slide is to explain that failure detectors are not just for the sake of detecting failures. A reliable failure detector is a central piece of distributed systems and can indeed be used to accelerate other distributed services in practice. And we did that, and we use our failure detector to improve a safe replication of the Redis key value store. Basically, having a reliable failure detector allows us to tolerate more failure with less nodes, and therefore resulting in performance improvement. You can see here the green line and the purple line that are improving over a deployed version of Redis, which is called Redis Raft, for safe replication, and improve throughput and latency with respect to this. So this is, I'm not going to go into details, but it's just to show that failure detectors can indeed be used to improve services such as a key value store. So it's not just, the improvements are not just to detect failures quickly, which may or not be beneficial according to the occurrence of the failure, but are a building block for implementing simpler and more efficient services. Okay, so just doing a results analysis, strong reliability can be achieved with deterministic or synchronous interactions. Our failure detector is fast because reliability is tightly linked with performance and speed and improvement. And our failure detector can simplify and accelerate coordination services, as it was the case for Redis, the replicated key value store with safe replication. Also, the system achieves 100% more throughput than similar work in this field, which tries to achieve similar work trying to achieve synchronous end-to-end interactions between in a data center system. So those were our current results. I will now go through our current work. So what are we trying to do now? We want to evaluate the impact of the system of our solution in terms of performance and energy consumption. As you probably noticed, we make some explicit reservation, and in order to achieve this synchronous interaction, the cost that we pay is resource reservation. It's dedicated core, dedicated pipeline for send and receive, etc., etc. So what's the cost on the system, and how does it compensate with the savings in the performance of the algorithm on top of the failure detector, for example? The second part is using synchronous interaction beyond failure detection. So can we improve them further? And then our current work stream is basically using going more towards hardware rather than software. So this is a pure software work. We want to use SmartNIC in network computing capabilities and perhaps work with the new TAP hardware to try and achieve better performance for synchrony. Okay, so this is what I just said. Basically, synchronous interaction for better services beyond failure detector, because a huge number of applications can indeed benefit from selective synchrony. And we want to use the synchronous subsystem for a limited number of services. That's why we use the term selective synchrony, because not a whole data center synchrony is just dedicated only for applications which need it. And then there's other applications such as security and real time, but we're working towards establishing this synchronous data center layer. I believe the term sort of depicts the picture of having this selective synchrony as a building block for better services, better coordination services, and we have here. I just want to present the motivations for us to go with this reliable failure detection and synchronous interaction towards hardware. We have previous work on offloading interactions to a SmartNIC. And you can see in this, please focus only on the diagram, not on the numbers. We can see how the latency in a SmartNIC compared to software only is much less jittery. We have very well-defined lines of latency, which actually correspond to the clock of the SmartNICs and exactly when that was timestamped. Compared to the software, which has much more mixed results because of the OS and other jitter introduced by software. And the same you can see on this picture on the right. Early benchmarks of FPGA-based SmartNICs in a peer-to-peer setup show that the latency is very tight, but most importantly, the jitter, the variation of this latency is also very, very tight. So these are our motivations to research more into hardware and the current focus of our work. And I want to terminate with this presentation with a discussion. So combining failure detection and synchronous interaction with the time appliance project. So of course, the most, let's say, benefits from having very, very accurate clock synchronization in a data center is that clock drift is a factor in how we determine latency, how we determine max latency in several protocols. So we have this clock drift, which is part of our calculation to get this upper time bound or to have some protocols synchronized. So the tighter the clock drift, the smaller our synchronization, our upper time bounds can be. So I'm thinking of something, maybe we can use time card appliances or similar things to improve on this, on our bounds even more. And another talking point is using this tGPIO. So I couldn't find many information online on this. I just saw some posts, but I saw as recent achievement of the OCP TAP the introduction of this tGPIO pin for clock signals directly to the CPU. And so basically this is of high interest for us, because a big problem in our project is how to send early notification to the CPU directly. And you can think of this failure detector heartbeat actually as a clock, because we send periodic heartbeats to multiple processes, and that do not have to be delayed. So it can also be seen as a clock. So I was reading with interest this tGPI topic, and I would like to talk about it. And because a very primary requirement of this is of our application is to bypass as much jitter as possible. So if we can bypass the PCI jitter, the OS jitter, and everything that's on the way by accessing directly the CPU, that's a very clear application of a time appliance project to our context. And with this, I end my presentation. So thank you very much. I hope this interested you, and I left my contact on the slide. So thank you. If you have any questions or want to talk about anything, please do.
Thank you, Davide, for this informative presentation. So let's open the floor for questions. Now you can unmute your microphone.
Yeah, so I have a question, Ahmed. For Davide. So Davide, when do you plan to integrate your synchronous stuff that you presented here with the TAP project using the time card?
When do I plan? There's no plan currently. It's under discussion. So the discussion is how to best do it. So we're trying to seek applications and common working points. So this is what I presented is just some ideas. As I said, I'm not really familiar with the current status of development, but I believe there's some common ground. So I wanted to hear from you. There's no date for that, but if we can maybe find some common ground, I think we can find some interesting use cases for the time card.
But you implemented your scheme on a smart NIC, right?
Yes.
Okay, good. Okay.
All right. So maybe I don't know. I give a follow up. Like, so Davide, if hardware gets available to you, you can start, let's say, some implementation, right?
Yeah.
Okay. We will have hopefully soon the first vendor who has tGPIO out of the box for real. Like I have pictures now out of the box. You know, open the box and the thing is right there, available. So.
So can you explain to me, please,
yes.
just briefly, what is this tGPIO about? So it's really
yeah. Sorry, go ahead. Sorry.
Go ahead, yeah, please.
Yeah. So tGPIO is basically like there are two pins, or it can be just one. The concept can be just one, and like this, like it's basically a time-aware input and output, right? General purpose input and output. So for the input, very simple. When you have a toggle, you will create a timestamp. From what? From the counter that's available to you. What's the counter available to you in the CPU? Is the TSC, or Intel likes to call it ART, always running timer. Now, the output works this way, that you give a time in the future, and when you reach that time in the future, you create a toggle on that pin.
Mm.
So it's not assertion, it's just a toggle. So you're basically getting an edge. If you start from the beginning, you know what's going on, then you have a deterministic thing, but usually don't count on determinism here. You just have basically a toggle. Now, with PTM, precision time measurement, you can have the NIC. NIC has a NIC that has PTP enabled, has something called a PHC, physical hardware clock, which now the same physical hardware clock that is used to timestamp packets over the layer 1 of the Ethernet is going to get also used for packets going over the PCIe bus. This is PTM, right? So then there is another part for PTM, which is on the root complex, which also does the timestamping with the ART, the always running timer, or TSC, right? So now that you have hardware timestamping on the two sides on the PCIe bus, you just need like this T1, T2, T3, T4, which Kevin basically came up with an elegant way to just keep it simple, just like 2 messages, essentially. And you get, aside from the details, now you have a projection with 2 values, a linear projection from the PHC on the NIC to the ART. Now, if your NIC happens to be synchronized by a PTP, or if it's not a NIC, is a time card, and the time card gets the time from GPS and back by atomic clock and all of these things is on that side and provides a time for you, the projection to the TSC, your TSC with a very low error is projecting UTC. So now anything you do is with respect to a global time scale. Of course, with the errors, with whatever errors you have. But the errors, because everything is hardware timestamping end to end, you can expect it to be under 50 nanoseconds. And as applications show up, I think Intel folks have nothing against it to make it even tighter and tighter. I mean, I'm promising on their behalf, but I'm pretty sure giving them a nudge, you know, you guys are fine. You're going to do it, right?
Thank you, Ahmad.
So that's basically the what TGPI is. So TGPI initially, I think, was, I mean, Kevin definitely, Kevin is here. Great, Kevin is here. So Kevin is the father of PTM. So I'm basically setting the stage for Kevin. So as far as I understand, Kevin should correct me. Like TGPIO was first there only to validate how good PTM is, but that's when the sidekick becomes the real thing, you know? And now, like, we see more applications showing up. Like, I mean, I use TGPIO to do like all kinds of measurement on software performance for how things are happening in a stack. Like I have current measurement versus TGPIO. Like, how cool is that? So leave it to Kevin to correct whatever I missed. You're muted.
Now can you hear me?
Yes.
Yes, Ahmed's always the best advocates for these technologies. Thanks, Ahmed. I did have a question. So I think it was interesting, if I'd love to be interesting to have a follow-up, David, as well. It'd be interesting. But on the bounded latency, the latency between systems from software to software across the network with some kind of worst case bound that you really want to achieve. That's very interesting because it's not something that it's more about cyber physical systems that I've seen that more predominant, at least historically, where you have a cycle time, and because of physics, you must meet the deadline. Otherwise, the actuator doesn't get the command in time, or right, you're not closing the loop in a deterministic way. Is there a characterization of that bounded latency that you want to achieve that would include some number of nines of reliability, where at some point the benefit starts to fall off the cliff in some way? For example, if you could meet a latency with 99% certainty versus you need 5 nines, or is 1 9 enough in some cases? Is that a knob that you've looked at turning in terms of the overall benefit that you get for the failure detection?
Yes, definitely. Thanks for the question. Definitely is something that we looked at. So most current works really focus on, let's say, a number of nines. But what we want to achieve here is really the 100%, which is a scary number. But the whole idea of these synchronous protocols and failure detection is we cannot afford to have a packet that's excessively delayed. So even the 99.999 take as many nines as you want, we really focused in our work to achieve as many nines as possible up to 100%, because that's we let's say we put the complexity there to then have a system that is reliable and the benefits ripple up top the stack, thanks to that reliability, because with reliability you can build more efficient algorithms, and simpler, which is also another very important property. So that's why we shifted the focus of many, let's say, high throughput, low latency frameworks that just optimize the average case latency. They don't care about the nines. We do care and try to push it as high as possible.
Okay. Very interesting. Yeah.
Thank you.
So I have a question.
Go ahead then.
So actually on 2 slides, on one slide you presented something about Falcon, and I think that's an overused terminology. I'm wondering which Falcon you used.
Yeah, sure. It's reliable failure detection is it's a similar work on reliable. Let me bring back the slide.
This isn't the Google OCP Falcon. This is something
It's not
else.
the Google OCP. No, sorry,
Okay.
probably I wasn't too clear.
I think that
It's
Google calls it Project Falcon.
Yeah, they have a reliable transport, and so and they
No,
donated it
it's-
to OCP, and so
It's no. It's a reliable failure detection by University of Texas.
Oh, okay.
It's a 2011 paper, but it's been the basic of modern reliable failure detection, and despite being from 2011, it still appears to be one of the leading failure detectors
Okay.
out there.
Good. Second question was, you showed DPTK in your results. What exactly did you do with DPTK?
We measured the latency. Let me bring back the slides 1 second. DPTK.
So that one had Falcon.
Yeah. DPTK in perhaps this slide, right?
Right. Yeah.
So this is previous work.
Mm-hmm.
So what was measured, that so it's not seen. I cropped the picture because I just wanted to focus on these 2 graphs.
Right.
So basically it was compared against DPTK. So we also measured the latency by just using DPTK. We can achieve good latency, but the problem is again the jitter. So DPTK does not have by itself jitter guarantees, but
Right.
this is previous work done by our group, but not directly by me. But I believe that was.
But was it done over like a PTP network using PTM at the processor, or was it just a general DPTK?
I think it was kernel level? I'm
Okay,
not sure,
okay.
sorry.
Okay, okay. I think I understand. Okay, thank you.
Thank you.
Right. Any more questions?
One observation I have is that reliable failure detection, and it could possibly enable error correction. Have you considered this direction?
Error correction in what context, sorry?
So if you have you have reliable failure detection, and this is in the context that we're looking at as timing, right? So the context is timing. So if you have a reliable failure detector, we can reliably estimate the failure rate. We could possibly come up with some sort of interpolation to have a correction of that error rate, right? To reduction of the net error rate over time, right? So no pun intended. Have you considered going in that direction, or?
No. Yeah, as I mentioned, I'm pretty new to this whole time application, but that's very interesting to hear. So
Because
definitely.
I was just thinking when you were talking, like one of the dimensions here, more accuracy, but another dimension is that whenever we want to push this higher time resolution down to simpler devices, right? And lower cost devices. And so to do that, perhaps error correction could be something that would help in that economic transition to lower cost devices and higher resolution timing.
Definitely. I will definitely look into that. Could you perhaps?
We told.
Yes, thank you. Great talk. Thank you very much. One quick question relates to the future work. You mentioned that you're planning on selective synchrony. Could you comment a little bit more on it, and specifically, how will you drive it? How will you measure it? How will you adapt? How you want to really plan on doing it better than what you have?
Yeah, thanks. Some question. So yeah, so basically, selective synchrony is the property of this, let's say, system layer. Think of the failure detector layer as the just basically an end-to-end system, which we can abstract as a layer, which provides synchronous interaction, synchronous messages. And how we plan to improve that is by, first of all, analyzing the hardware spectrum that we have there. So as I mentioned, this project was done completely by software, and we managed to achieve good results, but then with the accuracy of an upper time bounds of microseconds. But we believe that hardware, in terms of in-network computing or devices such as the time card, which have direct access to the message without going through the software stack, can provide even further synchronous guarantees. And so I think that is a very promising direction, but our work is also not finished in terms of the software. I think we can explore different solutions, and things are becoming more and more programmable. There's a lot of settings in Linux, for example, for real time. And so we are planning to explore both the software and the hardware space, which appears to be more promising, of this plethora of new technologies, which allows you for really deep in programmability, and these chips that you can put timestamps a bit as get timestamp very accurate timing as you guys do.
Yeah, I also feel that you can do even more by looking at the physics of the environment, physical environment, and start deep prediction of its behavior in the future. So you can really anticipate certain things to happen rather than observing that they have happened. So there's tremendous potential. Thank you.
Thank you.
Thank you very much.
I do have a question. Earlier in the presentation, one of the slides you mentioned you used a multicast to pass the failure detection status throughout the network or the devices. Are you talking about the network protocol multicast, or this is something new, something developed just for this?
Yeah, let me share the screen again. So, yeah. So this is so the multicast is just basic IP multicast of in a LAN in a network. But what's new is the protocol on top of it. So it's a periodic multicast which is deployed on a software-defined network. And the new thing, the novel thing with this approach is the traffic engineering approach that we use to minimize the traffic interference. So a node, a failure detection node, which is symbolized by the blue squares, cannot simply send a message at any rate or at any point in time. So this is our limitation. We have think of it as a rate limiter, which can get very, very short to the microsecond range periods. So it is in fact not a huge limiting factor, but it limits the sending the packets, and basically everything. The traffic engineering approach orchestrates everything and creates all these tunnels in the overlay network in order to ensure that we don't have queues at the same time. We don't queue, we don't have interference because there's no way that it's prohibited for the process to send at a higher rate. So in the example that I mentioned, before starting to send, there's a setup time, and the failure detection process asks the traffic engineering, the SDN controller, which does the traffic engineering, and that allocates a resource, which is the period, the transmitting period. And the failure detection process will comply to that. So in this sense is a novel protocol, yeah, but it's based on IP multicast. So the technology behind it is IP multicast.
Do you have to make a modification to the existing IP multicast protocol to achieve this, or you just you don't have to? Okay,
it's on top of it.
Okay.
Yeah.
Thank you.
Thank you.
I have one more question.
Just one second, let's see. Paul was.
Oh, okay.
I have a couple of questions, but I don't mind taking them one at a time. So, but first of all, David, this is a wonderful presentation. Thank you. I really enjoyed your whole story here and the connection to distributed systems. So my first question is, when you talk about jitter, what is that relative to?
Yeah. So jitter, we take jitter as the difference between maximum latency and minimum latency of the system. So the variation of the interaction latency.
Now, is that measured locally against a local timeline or local timer?
Yes, we all measure relative to a single host.
Thank you. And if I may, the second question is, can you say some more about how you would use those synchronous interactions as a clock?
So the analogy with the clock was more to get, let's say, to sort of more towards the TGPIO appliance that Ahmad mentioned, in the sense that we can think as we can abstract this sort of periodic heartbeat as a clock signal that it's ensured to come in at given rates. It might have some jitter, but it will never exceed this upper time bound. So in that regard, is a clock. I wouldn't use it as a clock. It was more an analogy to get closer to this idea of using perhaps something like time appliances or time hardware to have this clock signal coming in and use that as a notification for our failure detector. So if we have opportunity of using this novel hardware to get notifications in with very, very low jitter, that really increases the accuracy of our failure detection and really pushes down the boundary of this upper time bound. So it was more on that perspective.
Thank you.
Thank you.
Right. So someone else had a question. Sorry. Dan, it was you, right?
Yes.
Okay,
So you also, in your results, showed RDMA. What did you do with RDMA with regards to your results?
Yeah. So we measured against RDMA to prove that basically RDMA is not a panacea. It's not like the medicine for everything with regards to latency, and RDMA is fast, and it's indeed the faster approach. So we basically used this benchmark that you see here on the left. We basically measured the latency of RDMA packets out of the box using a default RDMA implementation for Rocky. And we noticed these fluctuations in latency despite the average being very good. So that's just to prove that you need to take a step further if you want to establish really synchronous, stable interactions. That being said, so we picked XDP as a technology here for kernel bypass.
Right.
It is also possible to perhaps use RDMA or integrate RDMA with our other engineering, let's say, to achieve the same stability. But we haven't tested that. So this is basically just a test against de facto standard implementation of RDMA.
So what was RDMA missing in your mind?
Isolation. It's definitely a crucial step, and also it's a little. I think RDMA has great possibility because in terms of kernel bypass, it's one of the fastest approaches out there. So I would say that the major factor is isolation, yeah, and yeah, possibly some. Yeah, I would stick with isolation. Yeah.
Okay. Thank you. I appreciate it.
So in the SDN switch that you're using for your experiment, like what OS are you using? Are you using an open source OS or some proprietary OS?
OpenFlow.
You're using OpenFlow, okay.
Yeah.
And from SDN controller, right?
Yeah.
Okay, thank you.
So I have a question. Did you think about using machine learning to predict failure and then prevent it from happening, which seems to be better than waiting until the failure happens and you detect it and then you detect it quickly?
No. This work is purely systems, so I haven't thought about machine learning for failure prevention. But I'm a bit skeptical on adopting machine learning on this type of applications. I'm gonna be honest, this is really like detecting perhaps sporadic failures across a long time, and the fact that we can react to the microsecond level does not impact our system too much. Actually, we are able to with such a failure detector, you're able to recover in the microsecond scale, which is really small, and we assume that the algorithms on top can recover from failure. So there's not catastrophic failure. If something fails, we can recover from it. So adopting a machine learning approach on top of this for prediction, it's a valid idea, definitely, but I'm not sure if this is the right scenario.
Okay, thank you.
You're welcome. Thank you for the question.
Any more questions?
So how does this, I guess, transpire to actual deployment scenario in the data centers? What's the next step?
So in terms of deployment to data centers?
Yes.
Well, we don't have, I mean, this is done as part of the work with SAP, which has data centers, and perhaps it's let's say it's not currently deployed in production, but and also we'll need some iterations, let's say some development iterations before being fully deployed in data centers. But we hope so. I mean, our current step is we're under the process of publications. So we're waiting to hear the outcome, and then based on the feedback from the community and on the interests, we'll assess whether that there's interest for this kind of solutions in real data centers. We certainly hope so.
Yep. Thank you.
Thank you.
Any more questions? Great. Hearing none, we'll adjourn, and we'll have you guys hopefully attend in 2 weeks next talk by Dimitrios Matsakis about what is time. Until then, wish you a good rest of the weekend, and we'll see you in 2 weeks. Bye, everyone.
Thank you.
Bye-bye.
Bye.
Thank you.
Thank
Thank
you.
you, David.
Bye-bye.
Bye-bye.
All right.
Bye.